Assalamualaikum and good day. So today we are going to learn something new, which is called substituted carbonyls. This is another type of pi-acid complexes. So for the first one, we're going to focus on phosphine-containing complexes. So for phosphine complexes, it must be attached with phosphine ligands. Your phosphine ligands can be present in these two kind of formation. It's either in the phosphine form, PR3, or it can be in the form of phosphate form. So POR3. So phosphate with oxygen, PR3 without oxygen. So these phosphines are ready to replace your carbonyls. Why it is ready to replace the carbonyl? There are three reasons. Number one, because it does have a lone pair on phosphorus. So in order to be a pi-acid ligand, your ligand must be having a lone pair. So it is ready for sigma donation. So this is called highest occupied molecular orbitals or HOMO. Second, phosphines is having empty orbitals of the pi symmetry. So which could be the d orbitals on p or the antibonding p phosphorus to carbon or phosphorus to oxygen in the phosphate form. So this is your LUMO or lowest unoccupied molecular orbital. So we have a lone pair. For sigma donation, you have empty orbitals, which is your LUMO. And the third one, we have filled pi orbitals. So it depends on the type of R that we have. R here, meaning what kind of alkyl or aryl group that attach to your phosphine. So it will determine what kind of filled pi orbital that you're going to have in your ligand, consequently in your complex. Now, the donor acceptor ability of these ligands, as I said, influenced by the identity of your R. So if your R is having a very greater tendency to pull the electrons towards themselves, or we call it electron withdrawing ability, so this will make your ligands or your complex even more receptive. Receptive as in, remember when I told you in the formation of carbonyl complexes, you must get your ligand ready to accept more electrons from the metal. How to make it so? By making it more or slightly positive. So this is only possible in this case by having electron withdrawing group. So your electron withdrawing group will pull the electrons from your ligand, so making your ligand slightly positive. Once it is positive, it tends to receive more electrons later from the metal. So based on IR and MR studies, these are the general receptor order for pi acidity of your ligands containing phosphorus. Now, the first one definitely PF3. We all know that fluorine is the most electronegative atom in this world. So when you have fluorine attached to your phosphorus, it does have the greatest electron withdrawing ability. So that's why it will make your ligand more receptive. And then followed by chlorine. You know that as you go down group 17 or halogen group, the electronegativity decreases because the size of your atom increases. And then followed by OAR. AR stands for aromatic, O, definitely oxygen. And then definitely aromatic works better than your alkyl because your aromatic does have resonance or delocalization of electron, which makes it more electron rich as compared to your alkyl. And then you have phosphine attached with aromatic and phosphine attached with any alkyl group. So you don't have to really memorize this, but of course you have to know the order. So in order to understand the order, you must understand the electronegativity of your group, because from the electronegativity, you will understand the ability of your group in pulling the electrons towards themselves, making your ligand more receptive. So that's number one, electron withdrawability of the substituent. And the second factor would be steric factor. So we had learned this steric factor earlier, but now we are going to measure this steric factor And the term that we use here is Tolman cone angle or theta. So this will measure how big the angle is. So the smaller the cone angle, the better it is for the ligand to form a bonding with your metal. So the bigger it is, the harder it is to form bonding with your metal. So, but how big or how small? So we have a cutoff here. So for angles between 140 to 160, these normally will impose significant static effects. If you have less than this, then you don't have significant static effect, meaning it will be easily forming bond with your metal. But if you have more than this, or starting from 140, it's going to be a little bit difficult. So from this table alone, we can understand that starting from ppH3, okay, your phosphorus attached with phosphine. In this case, we have 145 Tolman cone angle. So starting from ppH3 up to here, 194, you can see these three ligands are going to have some difficulties in forming bonding with your metal. So what the conclusion that we can make here? That if you have big groups attached to your phosphorus, you are going to have static effects. Consequently, you will impose some difficulties in forming bond with your metal. Okay, so we learn two factors here. One is the ability for your group to withdraw the electrons. So the strength of your electron withdrawing groups attached to your phosphine will determine how ready, how receptive your ligand is going to be. So if the electronegativity increases, the withdrawing ability of course increases, and hence your ligand will be more receptive in receiving more electrons from the metal. And second, we learn about static factor. The cone angle is now measured by Tolman cone angle. The bigger the angle, the more difficult it is to form bond with your metal. So the cutoff is 140 to 165. If you have less than that, so you don't have any problem to form bond with your metal. So I hope you do understand the concept of substituted carbonyls, meaning you can substitute the carbonyl to something else like a phosphine or phosphate. And for phosphine and phosphate, the strength of your phosphine and phosphate is determined by two factors. One is electronegativity or electron withdrawing ability, and second is the static factor. Second, we are going to learn carbonylate anions. Before this, we learned carbonyl ligand. So when I say carbonyl, it is neutral, zero charge. Now we have carbonylate anions. So carbonylate itself, without the term anion, we understood that it is an anion. So ATE, 8 means we have oxygen and it must be negatively charged. So we can prepare this in situ, which can be used to for further reaction without isolation. So can you find the meaning of in situ? This is going to be your first question today. So they can, first one, act as Bronsted bases. So if you still remember, we have learned three types of acid and base. We define pi-acid ligand based on Lewis definition of acid. Now we have Bronsted base. So what it is? You can see from this reaction, we have cobalt, and then we have carbonyl, negatively charged, carbonylate, and then this carbonylate complex is actually now has become more receptive in accepting proton. So it will form acid here. In fact, this acid has a similar strength to your HCl. So you see from this reaction, we understood that for a compound to be defined as a Bronsted base, it must be able to accept a proton. This proton acceptor, it is Bronsted base. But can you help me find the name of this compound, please? What would this be called? Okay, And second, it can act as a good nucleophiles. So in organic chemistry, I am pretty sure that you had learned what nucleophile and what electrophile is. So let us see how does this work in our syllabus. So of course, with certain regions, we can um, form another complexes. So first, it can react with alkyl halide. So if your carbonylate now categorized as nucleophile, so your alkyl halide in this case is an electrophile. So it will remove iodide away. So metal will be attached to your complex. So this is the product. Okay, so Me is metal anyway. So reaction with acyl halide. So please make some correction here that your alkyl halide should be should be acyl halide here. MECOI. Please remove this. And then I remains, but MECO to be replaced with your AC. So your AC in this case is CH3CO. Okay. So when you react with this one, you're gonna get another carbonyl complex. So iodide to be removed away. So the third one, production of heteronuclear carbonyls, meaning from one mononuclear carbonylate, you can form polynuclear carbonyls. So this can be done when you react rhenium bromide pentacarbonyl. So you are going to get your polynuclear carbonyls. So from this uh, session, I would like to emphasize that your carbonylate anions complex can actually form acid when it acts as a Bronsted base. It is also a good nucleophile, reacting with alkyl halide, with acyl halide, and also with some other metal complex to form heteronuclear carbonyls. Now let us see how to prepare your carbonylate anions. The first one is base-induced redox reaction. So base-induced redox reactions. There are two important terms that you have to learn here. One, it is base-induced, and second, it is redox reaction. So base-induced meaning the reaction will only take place if you have base. So this base is indicated by the presence of hydroxide here. So second is redox reaction, meaning reduction and oxidation are taking place at the same time. So you have to prove that in this reaction. So we have hydroxide and we have your carbonyl complex here. Carbonyl complex is used to prepare carbonylate complex. So from this state, you will become negatively charged. So we understood this quite obvious here that your Mn from 0 state, now it has become 2 plus. So meaning your manganese has been deoxidized. But the very question that we need to answer here, what would happen to your hydroxide? Would it be, or has it been reduced in any way? So can you prove that? That's going to be another question for you to answer. The second is reaction of metal carbonyls with reducing agents. It should be T here. Okay, such as sodium. But normally sodium is used in the form of amalgam with mercury, for example, because sodium alone is quite reactive. We do know that, okay, since secondary school, when you did carry out the experiments of your reactivity of your first groups of metal against water, so you could see that sodium is quite reactive. So that's why it must be used in the form of amalgam. So when you use this with THF, tetrahydrofuran, at 65 degrees Celsius, you're going to get your carbonylate complex here. Okay, so and then the third one, how to prepare carbonylate anions by having substitution by anions. So you can use KCN here. So the anion is Cn. Cn is cyanide. It is negatively charged. So it can replace your carbonyl. So you have 5 carbonyls here. You see, upon completion of the reaction using methanol as the solvent, you could see that you have 1 carbonyl last here, and this carbonyl is actually replaced by cyanide. Okay, so you're going to get carbonylate complex here. Okay, so that's all for this video. Stay tuned for the next video. Thank you very much, and don't forget to answer the questions that I have asked throughout this lecture, and please put it on the Padlet. Thank you very much. Assalamualaikum.